Okay, so today's 18th. Okay, so we have seen, so have you checked that S2 is a smooth manifold? I have checked one in the last class. Check one of the I have checked one of the tangent functions, but I told you this one an exercise to check others. So I hope you have checked. If you have not, you'll be in trouble later. In any case, so let's similarly one can see that Sn, more examples. Sn, which is x0 xn in Rn plus 1, such that x0 square plus x1 square plus xn square equal to 1. This is also a smooth manifold. All right. So what will be the charts? Yeah, what will be the charts? How many charts actually you can consider?
Sir, I think it is n plus 1 dimensions, right? And we take 2n+1 dimension charts. We take
No.
each coordinate greater than 0 and less than 0.
No, this Sn, yeah, so that is true. So Sn has dimension n, all right? But we are looking at in Rn plus 1. But you are right, you need to look at every quadrant, every half space, and intersect with Sn. So something like, let's say U1 to be Sn intersection x0 xn in Rn plus 1 such that x0 is greater than 0. All right. Well, similarly, you can you too, or rather, I should put it to make it in a way. So let's say u01 and u02. 02. Notation is little complicated, but you can actually write all the charts in that way. So Sn intersection x0 xn in Rn plus 1 such that x0 is less than 0, right? Similarly, you J1, so you define this way. Sn intersection. So what will be this subspace? What will be this subspace? This is x0 up to xn such that
Xj greater than 0?
right xj greater than 0 and uj2 is nothing but x naught up to xn Rn plus 1 such that xj less than 0, right? For j equal to, you can take j from 0 to n. So first one is already explicitly given, this one is explicitly given, but you can write it in this form. Now in a similar way that we have done for S2, you can show that this union covers Sn, and of course the projection maps will be the homeomorphisms, and then you can look at transitions map as well the similar way. No difference as well, just a few coordinates will be an extra thing. Other computation, the idea is exactly same. So please do this as an exercise to complete this one. If I go doing this here, the whole class will be gone. So so exercise, uh, exercise. Check that. So define. Oh well, I should give one more thing. So UJs are given, and so I let me define VJs also. Then I'll give the exercise. So Vj from Uj to Rn. So what will be the coordinate map? Or what will be the map? X naught, x1. You have xj here. Xn is equal to.
Just drop xj and put all other coordinates.
Right. So x naught dot xj minus 1, xj plus 1, xn. All right. Similar. I mean, it is as similar as you have seen there. So for each j, so for j of 0 to n, you define this. Now exercise is check that the set uj comma pj, j from 0 up to n. Sorry, uj1 here, right? uj1, pj1, and similarly, I mean, well, you put pj1 here also, and pj2 you define from uj2 to rn as similar. pj2 x naught, x1, xj, xn is equal to x naught, xj minus 1, xj plus 1, xn, right? So same map. Just since the domain is different, we have taken this one. So this set the collection uj1 or ujk, vjk, k is 1 2, j start from 0, ends at n. This collection forms and atlas for Sn. Okay, so once you show it, you conclude that Sn is a smooth manifold. Okay, so this is to check. I'll give another proof of this one, showing that Sn is a manifold, but in a general setting. Okay, and that is the next example. Right. So next example is the following. So consider a function rho. Let's say rho is a function from Rn to R. Right? Rn to R, you know what is C infinity means, right? Let be a C infinity function such that rho, gradient of rho at x is non-zero for all x in, well, yeah, let's write first for all x in some set. I don't want this to be whole of Rn. I want, let's say I want for all x in rho inverse zero. I want this part only. So rho be a C infinity function. This is not zero. Uh, one need two conditions. So let me put in this fashion, such that one, rho inverse zero is non-empty. Second thing is gradient of rho at x is non-zero for all x in rho inverse zero. The conclusion is then rho inverse zero is a smooth manifold of dimension so any guess what will be the dimension? Just a guess. I don't argue. I don't ask for an argument.
It is a closed hyperplane, like
Yeah, what will be the dimension?
one dimensionless.
Right. Yes.
Hmm.
So this is n minus one. All right. So and now if you show this one, then you can prove Sn is a smooth manifold by using this, right? This example. This you can think of this as a result as well as a theorem. But this is literally very simple, and the idea to show is or to prove is use implicit function theorem, right? Yeah. So what is the statement of implicit function theorem? Does everybody remember the implicit function theorem?
Yes, sir.
Okay. So what is it?
So we have a function from higher dimension to lower dimension Rn plus m to Rn.
Mm-hmm.
And then we are looking at the place where it is 0, and we are
Mm-hmm.
telling how the the m parts in the end, the
Mm-hmm.
first n parts are related to the last m parts. So the
Mm-hmm.
first n parts can be written as a function of the last
Mm-hmm.
m parts, and this again will be a continuously differentiable function. So for this to hold true, we need to look at the derivative at the point and look at the first component, as in the n cross n component, and check if its derivative is a different determinant is non-zero.
So they say that again.
So we have a map from
Mm-hmm.
n plus m dimension to n dimension.
Mm. Right.
It's a continuously differentiable map from an open set,
Mm-hmm.
and then we have its derivative at a point e comma
Mm-hmm.
b in like that open set.
Mm-hmm.
We look at its derivative. If the derivative's first component, that is the n cross n component of it, it's an n cross m matrix. So the n cross n component, if it is invertible,
No, it
then
is m plus n cross n, right?
yes, sir. Yeah. So n cross n component, we need to look at that part. If that is invertible,
Yeah. Yeah.
then what we can say is for every ending part, if we consider x comma y as an x is a n tuple and y is a m tuple, so every point in E is of the form x comma y.
What is
So
E?
E is the open set we took in n plus m.
Acha.
So for if we look at the set of solutions as that f of x comma y is equal to 0, then
Mm-hmm.
given y, we can uniquely determine x.
Yeah, that is true. Yeah, right, right. So how many of you are actually confused about reminding the implicit function theorem? How many of you get confused? Speak up. I know it is confusing. I mean, if you don't say anything, that means either everybody is confused or nobody is confused. Yeah, I think you guys, I mean, was quite outspoken when I taught you second year course. And I think suddenly a lot of pressure came and you stopped talking. Is it? Yeah. In any case, so it is the best way to remember is you consider a function. Let's say what would be my notation f from Rn or Rm cross Rn to Rn. Well, you take C infinity function, good enough. I mean, the best one you can take, C infinity. You fix an AB such that f of AB equal to 0. Fix a point in A where A belongs to Rn and B belongs to, well, here Yeah, for some A B in R M cross R N, which is R M plus N. All, yeah, but it is easy to remember because this one has to be same as this, right? Second thing, the main thing about implicit function theorem is about an assumption about the derivative. So determinant of derivative. So I mean here, see, when I want to write, you need to look at the components of f, right? So here you need to first fix the components. So if you consider x belongs to Rm and y belongs to Rn, then determinant of, sorry, I need to take a call. Hello? Yeah, I'm sorry this for this one. I don't know this. If I get some call from for mobile, it comes to these devices as well. Okay, so here determinant of the second component. So f has of course n components. So what would be the derivative matrix? Order of the derivative matrix? How many rows will be there? Yeah, maybe I should ask. Yeah, Abhishek, tell me how many rows will be there?
In the assumption, we need to take n cross n matrix. Uh,
No, f is given to you. I'm not taking. So what is the derivative? Derivative can be thought of as a matrix. So what will be the number of rows?
I mean, whose derivative are you asking? In the assumption, we need to take n cross n matrix.
No, 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 no. I'm not talking about the assumption. I'm taking the derivative of f.
Then it will be uh,
Number of rows.
n cross m plus n.
Yeah.
N cross m plus n.
Right. So number of rows is n. And number of columns is m plus n. Right. So here what we have is the I should, yeah. So this is a notation which is df, but with respect to y coordinate. This is now an n by n matrix. At what point? At AB, right? It's non-zero. Yeah. Is this fine? So next, what would be the conclusion? Then,
Sir, why did you write dy?
oh, because I have taken this coordinates from Rm as x and coordinates from Rn as y. So because of this, x I have taken from Rn and y is a coordinate from Rn. And that's why in the second quadrant. So y is y1, y2, yn. So it is a short way to write. This is derivative with respect to the part of the derivative with respect to y. All right?
Yes, sir.
Okay. So next is the conclusion. So what is the conclusion? So what do you get? There exist neighborhoods u of a and v of b and a C infinity function, let's say h, from u to v, such that what?
Such that h of a equal to b.
H of a equal to b. That's it.
And f of
And
x, and h of x is equal to 0 on u.
f of x equal to h of x.
Sir, I think f of x comma h of x is equal
Yes,
to 0 for all x belonging to u.
u.
Right. Right. So here you are right. So f of x comma hx is equal to 0 for all x in u. Right. But you now see uh, what happens to. So what you exactly get here. So we have seen this conclusion, right? So this is the conclusion. But think this in another way. So you think about this. So a little bit explanation. So this is nothing but. So consider u cross b. So where is it lying? Is it an open set first of all? And where?
It is an open set in Rm cross Rn.
Right. So this is open in Rn cross Rn. Right. Now here you can think of this instead of Rn cross Rm, here you can think of together. There to remind the statement, you think that way. But here you see in an open set in Rn plus n, right? And you now look at row inverse, you now look at f inverse of 0 intersection u cross v, right? So what is this set? What is this set?
Half of the function.
Mm-hmm. Yeah, here also you need to write this b equal to h of a, but that is not much of relevance in our case. Yeah. So what is it? Say it again.
So this is like x comma h of like graph of the function.
Right. So x comma h of x. Right. So x is in
U.
right. All right. So is everybody clear about that? Why is this so? Hmm? So if you're not convinced, better be convinced. So this is very important.
So you used C
Now,
infinity function, right? Instead of continuously differentiable.
which one?
Here in the statement, you use C infinity function.
Oh yeah. I have taken C infinity. I have taken smooth enough so that I get some smooth manifold out of it. No, that's why. I mean, you can work with C1. You'll get a function H to be C1 only. Okay, but most of the cases we'll see examples where function is C infinity smooth. So I've taken the statement in this way. So this part is so this C infinity is not required.
So, but you told even H
C1
is
is
C infinity.
enough. Yeah,
So you told even H is C infinity, but the
yeah. If
statement,
you take C infinity, you'll get C infinity. Yeah. The amount here you will take, the amount of regularity here you take, you get back in terms of age. So if you have not seen it, check it. Check, go through the proof and look at if you add one more smoothness, C2, let's say for example, and see whether the second derivative of h exists or not. All right.
yes, sir. So this can be
So
directly done in inverse function theorem also.
yeah, inverse function theorem also. Yeah, actually you have to go through proof of inverse function theorem and see there the amount of smoothness you put in the statement, you will return back the same amount of smoothness. If you add a real analytic, you will get back real analytic. I think, yeah, I think it's true. Yes. Yeah. And later on you will see, I mean, if you put complex analytic, you will get back complex analytic. Okay.
Yes, sir.
All right. So uh, let's now look at here. So why did I started with showing these things? So there is some importance, right? Now you consider this f inverse 0 intersection u comma v, you get this one. Now you can have this a map from this set, right? From this whole set, you can have a map to Rn, right? Phi, let's say. So what will be phi? Phi of x comma hx equal to. So what I want, let me tell you what I want phi. Phi to be a homeomorphism. So what will be this definition of this map?
H of x.
H of no, H is a just infinity map, right? This is X, right? X is in Prama. This is Rn. Sorry,
Oh, okay, sir. Okay.
yeah. This is Rn. So this is phi of x comma hx is equal to x. So you see this projection. So the point is here. So there exists a C infinity function here. This function is unique. You'll get a unique function. So in this case, so what I'm up to, a formation of certain charts, right? So this will give you charts. Do you see it? This u cross v intersection f inverse 0. This gives you a chart of f inverse 0. Does it make sense to everybody? Okay, let's look at in a simple example, which is the previous example. So this is, yes,
How it
yes.
gives a chart by just projecting it to h of x.
No, projecting it to x.
X. Oh, okay.
Switching it to X. And you see this is 1-1 map, right?
Yes, yes, yes.
This is 1-1 map. And this is of course inverse. You pick a X here, you'll get X comma HX,
Hmm.
right? That
Right.
is also continuous.
Yes, yes.
So this is actually a homeomorphism.
Yes. Hmm.
So this phi is a homeomorphism. So this gives you a chart. So now let's look at this example. As I mentioned here, just to looking at a single function, not more than one. Let's look at this. So rho was a function from Rn to R, right? And what we had, the condition C infinity. This is C infinity. Rho inverse 0 is not equal to empty, and gradient of rho x non-zero for all x in rho inverse 0. Right? This was the condition. Now let's fix a point first. Fix x naught, which is, what should I, no, we don't want x naught. Let's look at a, which is a1 up to an in Rn. Well, such that rho a is equal to 0, right? And by assumption, gradient of rho a not equal to 0 implies there exists j in 1 to n such that del rho by del xj at a not equal to 0, right? Yeah, this is fine. So what is the derivative? What is how many rows are there in this derivative? Derivative of rho?
Single row.
Uh-huh.
One
One
cross.
row, right?
Yeah.
One row, right. So one of the partial derivatives is non-zero, implies the gradient is non-zero. Derivative is non-zero, right? All right. So now, so without loss of generality, assume del rho by del xn at a is non-zero, right? That we can assume since one of them is non-zero. Now you think of rho as Rn minus 1 cross R to R, right? Yeah. So this we'll consider this x and y from R, right? Yeah. So we want to take this in the setting of implicit function theorem and try to see whether this condition holds. So this is C infinity. So what row of a1, a2, an minus 1. So this is a prime, let's say. This we can think of this a prime comma an is 0, right? So this a prime belongs to Rn minus 1. And this an belongs to R. Third thing is the partial derivative del rho by del xn, right? Or del rho. So xn in our case is just y. So del rho by del y at a is not equal to 0, right? So all the condition of the implicit function theorem is satisfied. Right? So what conclusion will you get? Yes, what will be the conclusion? Yeah, Aditya, what will be the conclusion?
Um, Sir, I'm not sure.
So I spent around 15 minutes saying what is implicit function theorem. Were you seeing that?
Yes, sir.
So I said all the condition of implicit function theorem satisfied. So what is the conclusion in this case? Okay, Arundhati, tell me. Arundhati, are you there? Yeah, I don't know what is happening. So I have explained what is implicit function theorem for last 15 minutes. You said everything is clear now. This is your turn, right? And if you're not clear, you just have to go and sit with it. Yeah, Devanjit, can you tell me?
Yes, actually, there exist two open set. One is
Mhm.
containing Rn minus one, and one is open in R. U
So
and
there
V.
exist neighborhoods for open sets.
U and V. U containing Rn minus one, and V is
Neighborhoods U of A1, A2, An minus 1,
and V in R.
and V of what? N in R.
In R.
Here in Rn minus 1. Such and
And a smooth function, let's call it F from U to V.
mhm. So let's call it H only.
Okay.
U to V such that
Such that row of An minus one, A1, A2, An, comma H of A1, A2, An minus one is 0.
no, that's not correct. Row of x comma hx is equal to 0 for all x in U. And of course, here An is h of A1, A2, An minus 1. Right. So this is a very basic thing, but this is important. So this is what is very important to remember, and you will see a lot of use of it even later. Okay, so this is this is what we get. Now Now what we want to see, rho inverse 0, as before. As before, rho inverse 0 intersection u cross v is what? So this is the conclusion of inverse function theorem in our case. So conclusion we got. Now later we want to see this one. So this is x comma hx, where x is in u. All right. All right. Now let's call it this u comma v, this open set, as u tilde. Call this u tilde a. Right. And well, I would rather call u tilde a as in the intersection. So this one whole thing, we call it u tilde a. All right. Now for every a in rho inverse 0, the above is true, right? So you define phi a from u tilde to, yeah, I should do that as well. So u tilde is given. Now phi a defined from u tilde a to r n minus 1. It takes x comma hx to x. Does it make sense? Everything is clear? It might look simple when I'm doing, but unless you go and sit with it for some time, it will not be clear. So this the for every, the point is, for every a in rho inverse 0, this is the above is true. So what does it mean? So you consider this one. Consider f ua tilde phi a, where a is in rho inverse 0. So claim f is an atlas of rho inverse 0, or atlas on. Does this make sense? So what is needed to show? What was the condition for being an atlas? Yeah, somebody say.
It should cover the space, and it
Yeah.
should be mutually compatible every two elements.
Right. This u tilde a, does the union covers a, covers whole of rho inverse 0?
Yes, sir.
Why?
For every point we have
Right. So for every point we have taken a neighborhood. So it definitely covers. All right. So it is actually uncountable collection of open sets. All right. So rho inverse 0 is actually union of ua tilde a belongs to rho inverse 0. That is definitely, it covers, right? So what is the next thing? What is the next thing?
Any two should be compatible.
Yeah, any two should be compatible. So how do you show it? Any two? So any idea? So compatibility condition, or rather to look at transition functions. So this transition functions to be smooth is a compatibility condition which is required. Yeah. So you need to consider, let's say A comma B belongs to rho inverse 0 be two distinct points. All right. Now corresponding to A, you have UA tilde phi A and UB tilde phi B are the charts around A and B. So this is the part actually which distinct where I differed from Tu's book. So this example is not there. So you need to look at notes. I don't know whether there might be some book it is there, but it is not there in Tu's. But this example is very important. It will allow you to construct so many manifolds. Okay. So these are charts around B. Compatibility condition means you have this, let's say UA tilde, you have UB tilde, and you have map here phi A, map from this is phi B inside some open subset in Rn minus 1. Here also it is in Rn minus 1. Right? So now you need to look at this map. This map, which is phi B compose phi A inverse, and this map, which is phi A compose phi B inverse. All right? And we need to show this to our smooth map. So what is, now let's compute. What is phi B compose phi A inverse? What is phi A inverse? So, and we will be looking at this place in the intersection. So A might be somewhere here, B might be somewhere here. But we'll be looking at this. So what is phi A inverse? Can anybody tell?
So it takes x and gives out x comma hax, where ha is a function we got there in implicit function.
Right. So phi A x will be x comma hx, but we put a subscript A because it is around A. This is the HA inverse. All right? Because phi A inverse. Phi A was the projection, and since for every x you have a unique x comma HAX, so it makes sense. Now if you compose, so let's say x, so it does x belongs to phi A of UA tilde intersection UB tilde. Look at this this one, and now we are looking at phi A inverse x. That is fine, no problem. It is actually true for phi A UA tilde. So now you compose with phi B, phi A inverse x. Since x belongs to here, this composition will make sense. So here phi B of x comma HAX. So what will be it?
X.
Is it x? Why?
Sir, if it was HBX, then it would have been X.
That is the point, no? That is the point. So there is a catch here. So remember here, we have, so let me go back to this slide. See, I have taken this one, right? The last coordinate. So in general, so when you change your A, it might not be the last coordinate all the time, right? So it will be the corresponding coordinates. It will be the corresponding coordinates. For example, it might be for HB, it might be some other coordinates inside. So it will not be all the time X, but it will be of certain forms like this. It will be of this form, the following form, like this, one of the following forms. So it might be X as well. It might be X1 up to Xj minus 1, Xj plus 1, Xn minus 1, comma, HAX, right? It will be one of the two forms. Does it make sense? So my point is the derivative with respect to the last coordinate might be 0 for B. Then what will you do?
So the
What
whole
derivative?
function might be different, no, sir?
No, not just for function. Actually, the component will be the different. You might not get the last component.
Sir, even if the component was same, still H is determined from the point. So the H can also be different.
Of course, that H is different, but that H was in place of Xj. HB, that is HB, right? That was HB. For B, you have HB. So HB will be in place of jth coordinate here. Okay. Yeah. So let's look at what is phi b. So phi b. So around B, maybe I should explain a little bit here. Around the point B in, so B is in Rn, right? So what happens around the point B? Since gradient of rho at B is also non-zero, so B belongs to rho inverse 0. So this implies there exists J such that del rho by del xj at B not equal to 0, right? So that is there. Now all the time you cannot take to, the last part. So in the beginning for the first I could do that one. So if A is not that point where derivative with respect to last coordinate is non-zero, you take other point where it is and name it as A. So you can start from one point, but now B is another point. Derivative of with respect to the last coordinate may be 0. But there will be some J where the derivative is non-zero. So by implicit function theorem, so what happens by the implicit function theorem? there exists a neighborhood of b1, bj minus 1, bj plus 1, bn in Rn minus 1, and there is a neighborhood, let's say u, u, and a neighborhood v of bj in R such that, and a function, and a function, C infinity function, hb from u to v such that h of b1 up to bj minus 1, bj plus 1, bn is bj, and row of x1, xj minus 1, hb x, well, xx I am calling that one. So here it will not be just x, it will be x1 up to xj minus 1, xj plus 1, xn, right? Each function of those variables, xj plus 1, xn is 0 for all x1, x2, xj minus 1, xj plus 1, xn in u. Does this make sense now? The coordinate at which you are getting the function, that might change. All right. So in this case, so what will be the map phi b? Phi b x1, x2, xj minus 1, hb x1, x2, xj minus 1, xj plus 1, xn, xj plus 1, xn is equal to this coordinate, which in the beginning I told x, but in this case it might be like this, xn. This is the projection. Projection on the variables on which rho inverse 0 is a graph. The variables are this. Jth variable, we could get the function hb. Now we have this one. All right. Now let's come back to here. So what will be it? It will be x in this case, where this, it will be one of this form, right? So it will be x if the last variable only, so hb comes into the last variable only. It will be this one, so hax will remain here. See, the jth variable will drop. But what you need, this is a smooth function. This is, but you need a homeomorphism also, right? So is it a homeomorphism? Oh, by the way, did I make any mistake here?
Sir, I think HAX.
Yeah,
Sir, where did
HAX
you
will not
apply
be there.
HB? You didn't apply HB, right? In the middle, there should be HB.
Yeah. Okay, so this one, when you go back to going back under phi inverse, you will get x comma h a x, and that is also lying in the coordinate u b tilde, right? In the coordinate chart u b tilde. So h b x is right there.
So in the middle, whatever coordinate was there, xj, for that we have to take inverse in the image, right? Like it directly won't come because we're putting phi of b.
See what you are putting?
So here we're just dropping xj here.
Yes, dropping xj because this one, this one will be, yeah. So let me write it. So this one will also be of this form, as I said here, will also be equal to as x1 up to xj minus 1 hbx. I mean, let me write it x prime, the other thing, xj plus 1 xn. So this is also this one, right? Because it is in the intersection, right? Well, so the coordinate will be different. This x and that x is different, right? So here you put tilde. So coordinate coming from the two sides are different. Here it is x. Here it is, let's say, x tilde. But this point x comma hax will also be of this form. So you need to look at this one and as this form and apply it. I mean, apply phi b on this. So this part will get dropped.
So I have one doubt.
Yeah.
That is of that form because the set we're looking at is the graph.
Yeah.
Okay, so because it's the graph, we have that form because that form is uniquely determined.
Right.
Okay, sir.
Yeah. And both of them comes from applying implicit function theorem. All right. And that's why I actually dropped hj here. Sorry, xj here, right? Because of this reason. And but you see here in the intersection, this last coordinate, if you look now if you look at this as a coordinate, so both all these things lies in Rn, right? All these things lying in Rn. So this is equal to this means you have this x1 tilde is equal to this. That thing holds, right? So since everything I mean, I was saying this is a different coordinate, but if you look at all the things lying in Rn, right? And we are looking at Rn only. So x comma hax is a member of Rn, and this tilde, this also is a member of Rn, and there I'm saying these are equal. So that means you have corresponding xj's to be xj's and x tilde j's should be same. All right. And this xn tilde will be hax. Does this make sense? And that's why it is of this form. Does this make sense? And other coordinates actually makes this as invertible. So check this one. So this is an exercise, but I'll explain again if you are not clear. So So check that. So check that phi a pb composed phi a inverse is a diffeomorphism or is a scene PD. This is smooth, right? So this is C infinity is smooth, and this is very clear, right? So this is very clear because you have HA. All right. See this all these coordinates are smooth, and HA is also smooth. So it is smooth. And if you look at the inverse of this, well, you look at this map. This is the inverse of this one, and so that this is smooth. This is also smooth. Then you are done. Does this make sense? So do that, the other computation. Check that this is smooth. And hence, this F gives us an atlas on rho inverse of 0. So, rho inverse 0 is a manifold, a smooth manifold of dimension n minus 1. So make yourself very clear about this example. So every time when we introduce something, we will definitely do for this example. And corollary to this, so this is done. Now if you look at row x1 x2 xn x0 x2 up to xn, so start from x0, so row from rn plus 1 to r. This is x0 square plus x1 square plus xn square minus 1, right? Rho inverse 0 is Sn, right? So from here also you can get Sn to be smooth manifold. So we proved actually generalization of that. So the here we knew the projection maps. So in this case here we knew the projection map exactly what it is. But instead of doing that, you can, I mean, this is known because we know things about sphere, and even if you don't know, we can, by implicit function theorem, we can say that this is manifold. This is a smooth manifold. Yeah. Any question here? So this is a very important example that you should remember, and you should be convinced of that this gives a manifold. Okay, is it clear? Any question? Okay, so next look at smooth maps. So this is the reason why we want to study manifolds. So why are we talking about atlas, differential structure, whatnot, all these things? Why? Do you have a reason? Any idea? Why are we talking about such things? Or why do we care about manifold at all? Yeah, what do you think? Any idea?
So that can map nicely into Rn and then we can apply some of the Rn theorems.
No, that is not the case. What the motivation is to define the smooth map, differentiable map, and do calculus on the spaces different from Rn. So whatever calculus you have learned in analysis 3, we want to do that calculus in the spaces which is other than Rn. For example, you can do those calculus in Sn, for example. Or some other spaces which does not look like Rn. Of course, but unit locally looks like Rn. So the structure, differentiable structure is needed because you need to define what a smooth map is, what a differentiable function is, and so on. You want to do calculus on those spaces. And that is why you require this differentiable structure. So first thing is, let M be a smooth manifold a function f from M to R is said to be differentiable. Well, smooth, since, and one can say differentiable or yeah, I can say actually differentiable. So it's said to be differentiable if for every chart U phi f compose phi inverse is a differentiable map. So when you talk about smooth manifold, you have already a differentiable structure. So charts coming from that differentiable structure. It's not coming from outside. Okay. And you see this one, phi, this chart map phi coming into the picture. Right? So let me draw this picture. So M is here, and you have R, and here, so suppose M is this space. For every point you have some chart, and you have phi here. Now this composition, which is F compose phi inverse, and this is smooth, this is differentiable. So it is not just differentiable, since I just wrote differentiable, but this is any differentiable, C1 differentiable, C2 differentiable, C infinity, if this hold the same thing. And this is now is from Rn to manifold of dimension n. So here it is from Rn, right? So this map is map from Rn, an open subset of Rn, open subset Rn to R. All right. Yeah. So we can, now you might have a question. So if we change the chart, what happens? At the same point, suppose you have you apply a different chart. Well, there is no problem. So if you have, if B comma psi is another chart, then you need to look at this F compose phi F compose psi inverse, and which is, you can, of course, you can see this F compose phi inverse compose phi compose psi inverse, right, on the intersection, right? On let's say psi of u intersection v on the intersection. So this is C infinity, and this is C infinity from definition of smooth manifold. So this also becomes C infinity. So the definition of differentiable function is independent of chart. All right. So can you tell me what is so what will be the definition for a smooth map between two manifolds? Suppose you have manifold M and a manifold N, capital M and capital M, and a map between capital M to capital N is said to be smooth if what happens?
Sir, I have a question.
Yeah, sure.
So you're like, is another chart. Shouldn't all the charts belong to the maximal atlas? Like
Oh,
we should take
sure.
the charts from the maximal atlas, right? Because it might not be. So
Oh, yeah. Well, here, I mean, of course, it is for every chart, but it's enough to consider only for the atlas, right? So here, of course, this I wrote for every chart in this case, but it is actually enough to consider charts of in an atlas. So you can't check for every differentiable. I mean, every chart, right? In a differentiable structure, there might be uncountably many.
sir, there might be a chart which is not compatible, right? But there still might be a
No. In a
maximal atlas.
differentiable structure, when you have a smooth manifold, a differentiable structure is given. So you have an atlas. So you can take any atlas in that differentiable structure. And you know that containing that atlas, you have a unique differentiable structure. That is the maximal atlas. Right?
Yes, sir. But what I'm telling is this needs to be from that atlas, right? U phi.
Oh, yeah. So here, what differentiable means here, that you need only to check this functions for an atlas only, an atlas inside the differentiable structure. So, I mean, M is not a map from a topological space. Already, a differentiable structure is specified by saying it is a smooth manifold. Now, every chart comes from differentiable structure, right? Now, what I'm saying is that you don't need to check every chart in that differentiable structure. Checking for one atlas is good enough.
So now that we have this U and phi, we can have a maximal differentiable, maximal atlas with this.
Yeah.
But what guarantee do we have that the new phi and the V phi you took will be compatible?
No. I mean, so the point is, if you have a space, first of all, and you have a differentiable structure on it, right? This too is needed to become some space to be a manifold, smooth manifold, right? Now, if you change this differentiable structure, the smooth functions will change. The whole class of smooth function will change. So if you change the differentiable structure and it is not compatible with other, if it exists, if you incorporate that one, functions will change. So
Sir, I'm
smooth
just
function
telling.
is with respect to a differentiable structure.
So it is dependent on the maximal atlas that we choose.
Yeah. It is actually dependent on the maximal atlas you already chosen by saying that it is smooth manifold. So you have specified a maximal atlas, but you don't know what it is, right? What are the charts in the maximal atlas? You don't know. These are union of all whatever compatible things, right? So what do you check for a function? So to show for a function f to be smooth, so you check for an atlas lying in the differentiable structure. So if you change the differentiable structure, incompatible thing, then your function, differentiable function will change.
Sir,
Differentiable function
once
is
in
the
the
classic
next
function.
page.
Yeah.
So you took V and phi as another chart.
Yeah, another chart inside the structure, differentiable structure. So
So, but
here another
we didn't
chart.
mention that, right? It's not. It may not be in the maximal atlas.
No, you when you are in a smooth manifold situation, you are not going out the differentiable structure. So for example, let me say you, so Milner has showed that in S7 there are 28, there are several, actually 28, several differentiable structures. So the same thing, you put differential structure, the derivative function will change, the differentiable function will change. Differentiable function with respect to one structure might not be differentiable with respect to other structure. So when I say another chart in a smooth manifold, that means the differentiable structure is already specified and charts coming from that differentiable structure. So another chart in the space, in the space, not in the manifold, then it might be different. So here another chart, let's say in the manifold, rather I would say, yeah, or in the differentiable structure, what you say. So when I say here another chart, it what I mean, or what it means here, inside that differentiable structure. So
Sir,
here, yeah,
the confusion I had, because when you define differentiable structure,
yeah,
you did not associate it with the maximal atlas. You were like a space which has a maximal atlas.
is it? Is it true? Can you check it? Check the notes.
Yes, sir. So sorry, sir. So maximal atlas is called as a differentiable.
Yeah.
Yes, sir. Okay.
So I mean, you must specify a differentiable structure to say this is a smooth manifold, which means in other words, you specify an atlas. That is good enough, and that makes life very simple because you don't need to go with this uncountably many charts. You look at the number of charts you are comfortable with, cover it up, cover the space, and work with it, and with the compatibility condition, of course. Yeah, is it fine now?
Yes, sir.
Okay, so no problem. So these questions might have clear doubts for others as well. So this is good. You should run. I mean, one should be able to understand that the motivation for studying manifold is to do calculus, do differentiability, all these things. Later on, integrability on the spaces other than Rn. So here it's our first step to define smooth function or differentiable function. We don't have now limit, quotient, don't have anything. All this there in Rn. Now, in terms of Rn, we are defining differentiable function right here in different spaces. Okay, so that's it for today. Yeah, any question? Any other question?